So today we read about some applications of double integrals. We've been seeing how double integrals can be used to calculate volumes. However, volumes are in fact not the primary way that we use double integrals, and here we'll talk about a couple of other places where they are used. So the motivating question is clear. Where else can they be used? The answer is lots of things. We'll go over a couple of examples primarily from physics, but hopefully discuss a little bit about how these ideas can be extended into other fields as well. So the simplest example is in calculating mass. So suppose we have a thin metal plate in a standard calculus textbook with a variable density sigma of x and y. Or if you'd like to be a little bit more creative, suppose you have gone to an all-you-can-eat buffet and you have a dinner plate with food distributed across your plate and different amounts of different foods, and different foods have different densities. And so you could construct a density function for the mass per square centimeter of plate of food on the plate. Whichever interpretation of the word plate you are using, you might ask the question, what is the total mass? And so here we have a sort of visualization of this idea. This is supposedly a contour plot of some density function, sigma of x and y. And colors more toward red are higher values, colors more toward purple are lower values. So we would have a lot of food stacked up on our plate in this region right here, or some very dense food. Here, a lot of dense food. And then here in the corners, maybe not so much dense food. Maybe the green beans go over here in the corners where the steak goes in the middle or something like that. You can supply your own interpretation. So how do we calculate the total amount of mass? And just at the risk of being pedantic, we will review the basic approach to calculating integrals in any context. This may be a particularly simple interpretation, but we will nevertheless go through the steps of constructing the integral. So the first approach is to slice the domain into subdomains. I won't draw that, but the idea is that we slice both x and y. They both have some range, and we slice them into pieces, and we get little area elements, delta A, of very small areas after we slice this, say in Cartesian coordinates, though you could equally do it in polar or any other coordinate system. The second step is to approximate the contribution to the total mass in each subdomain. So if we have sliced x with an index I and sliced y in an index j, then we have two indices. We have the mass of the ijth slice of area. And what approximately is the mass? Well, mass is density times area. If it's areal density, mass per unit squared of per distance squared. And so the total mass is density times area. So we have sigma, our density, in the square, xi and yj, or any point within that square, times the area of the square, which is delta x, delta y. And so this is our contribution to mass. Density times area gives us mass if the density is in terms of area. Finally, we construct the integral of all these contributions. The contribution from each slice allows us now to build the double Riemann sum, the sum over all slices of the approximate contribution from each slice. And then we take a limit as delta x and delta y go to 0, that is, as the area of the slices goes to 0. And this is the long version of what we denote as the double integral. So we see that mass of a variable density plate is the double integral of density times the area element dA. I want to emphasize that this does not have to be restrained to a physics problem. Density does not have to mean mass density. If you are more interested in alternative energy, which is an up-and-coming hot field, especially in Texas, where we have all kinds of sources of alternative energy, this could be energy density per square kilometer, solar energy density, or wind energy density per square kilometer or square mile of land. Essentially anything with units of something per length squared, as it says, can be integrated over a 2D domain and obtain the total amount of that something, because when we integrate this against dA, dA has units of length squared, and we get the original unit, the quantity in question. So for example, I'll do a worked example that has nothing to do with physics. This is farming. So suppose you have a farm, and the farm has different kinds of soil at different parts of the farm, and you have measured over the years and determined that the different parts of the farm produce different crop yields, okay, measured in kilograms of wheat or corn or whatever per meter squared. So suppose you know this function. You've done some measurements, you've done some testing, you have experience, you know that this function, this yield function, as a function of x and y on your farm, is some known function. The question is then, how many total kilograms of produce can you expect to harvest in a harvest season? Okay, so suppose our function is 100 kilograms per meter squared, plus 2x plus 1/10 y squared. So if x is east-west, then the east side of the farm yields a little bit more, and the north side of the farm yields a little bit more as well. And suppose your farm is 10 kilometers by 10 kilometers in the x and y directions. So this yield, y of x and y, is a produce density. I mean, you guess it's really sort of a mass density. It's a mass of produce, but we can think of it in terms of produce instead of just something like mass from a physics class. And so the total amount of produce is this yield function, produce per square kilometer, against dA. And we express this in Cartesian coordinates. So 0 to 10, 0 to 10 of our function, 100 plus 2x plus 1/10 y squared, dx dy. Now we just perform iterated integration. So we'll integrate first in x. The 100 becomes 100x, 2x x squared, and 1/10 y squared. This is like a constant. And when we integrate a constant, we get a constant times x, so 1/10 x y squared. Evaluated at x equals 10 and x equals 0. We get no contributions at 0, and so we plug in x equals 10 to get another integrand. We now integrate this in y to get 1100y plus 1/3 y cubed. Again, there's no contribution from y equals 0. We plug in y equals 10, and that gives us 11,333 total kilograms. A second application is to find not just the mass of an object, but to find what is called the center of mass of an object. And you may have run across this in your Calculus 2 class, but we're now able to deal with this in a much more satisfying way with double integrals. Suppose we have, again, a plate of variable density. It could be a rectangle, it could be some other shape, but a thin plate that has different amounts of mass at different points along the plate. The question is, at what point, x bar comma y bar, that's a particular point in space, where can this plate be balanced on one finger? And this point is called the center of mass. How can we calculate the center of mass? The book has a description based on moments. I'll present here a slightly different description based on torque. Perhaps they're actually the same thing, but this was a way that seemed more natural to me. So imagine that we take a thin rod at a particular value, x equals x bar. Okay, here I've tried to sketch this thing. We have a particular, the x coordinate, remember, is usually drawn coming out of the screen. And so this is a line of constant x. And we place our object on this line of constant x. And we will now calculate the total torque exerted by gravity on this plate about this axis, x equals x bar. Okay, so 3 steps. We slice our domain into small regions, delta A, with area delta x, delta y. We approximate the contribution in each of those small boxes to the total torque. And remember, torque is the displacement from the point about which you're rotating crossed with the force vector. Okay, so we will always be rotating about the position x equals x bar, and so the displacement from this line to any point x in space will always be xi minus x bar. So whatever xi is, we subtract x bar from it, and that will be the closest distance to this line from the point xi. And that displacement is in the I direction, so centered on the bar, pointing out toward the point in question. I'll draw a little point on here. So this is our point, and we now have a vector emanating from the bar to the point, and that is magnitude xi minus x bar, and it's pointing in the I hat direction. Now this must be crossed with the force. What is the force? Force due to gravity is mass times acceleration. So there's the acceleration due to gravity right here, g, but now we need the mass. What is the mass of this small slice of material? Well, we already saw that in the previous problem. That is sigma xi yj times delta x delta y, the density times the area. So that here's the mass, and the acceleration is negative gk. So here is the force equals mass times acceleration due to gravity due to that little slice of mass. So the torque from that contribution, we now cross these vectors together. We have a scalar g, a scalar xi minus x bar, a scalar sigma, and then we have two vectors, I cross negative k, and finally we have a delta x delta y, which I forgot to write, and this is going to be our contribution to torque, and when we cross I and k and I cross k and take the negative, we get j hat. So the total contribution, the approximate contribution to torque from that slice will be the constant g, acceleration due to gravity, xi minus x bar times the sigma times the area in the j hat direction is the axis of rotation. Now we just integrate the total torque. We take all these contributions from the individual slices, do the infinite sum over all slices, and take the limit as delta x and delta y go to 0. That gives us the following double integral. G is a constant. It comes out the double integral of x minus x bar, sigma of x and y, dx dy, again pointing in the j direction. So here's an integral for the torque. So what? If this line x bar corresponds to the center of mass in the x direction, then the plate will balance. That's the whole point. We're trying to find the point in space, the value of x and the value of y, at which this object will balance and not fall off. And if it's balancing, it must be the case that the net torque on the whole plate is 0. We just calculated the net torque, and so what we need to do is take this integral for the net torque and set it equal to 0. We can divide out the gravity coefficient, and we have the following, that the integral of x minus x bar, sigma of x and y dx dy has to be 0, where again we've gotten rid of the gravity coefficient and the direction vector j. Those are just constants. And if we're setting this equal to 0, it doesn't matter what these constants are, it just matters that the integral must be 0. Well, if that integral must be 0, we can separate it into two pieces. On the left we have x sigma dx dy, and on the right we have x bar sigma dx dy. But x bar is a constant. It is a particular value of x, which we are setting to looking for the center of mass, and so it can come out of the integral, and that allows us to finally solve for x bar by dividing both sides by this integral here, which is nothing more than the integral for the mass, which we already defined and called m. So when we divide through by the mass, we see that x bar is 1 over the mass times the double integral of x times the density function. We could do exactly the same calculation for a bar placed parallel to the y-axis at some fixed value of y, and we would find that the value of y about which the plate would balance would be y bar 1 over the mass double integral of y sigma of x and y. And these two numbers are called the center of mass with respect to x and y. This is something that is probably worth memorizing or putting on a note card. It's not trivial to rederive, and so it's worth just remembering that the x center of mass is x times the density. The y center of mass is y times the density, and the mass itself is just the integral of the density, which is needed to calculate the x and y center of masses. So we'll conclude with an example of this kind of calculation. We have a unit circle whose density has the functional form 1 plus x. So we have our circle, and the density is 1 plus x. Over here at x equals -1, the density is 0, and the circle gets more and more dense as we work our way toward x equals 1. So more of the mass is going to be on the right-hand side. We would expect the center of mass to be over here on the right-hand side, Furthermore, this is completely symmetric in the y direction. The top is exactly the same as the bottom. The density does not depend on y. So we'll expect that the y center of mass is in fact at y equals 0, and we'll only calculate the x center of mass. But first, we need the mass itself. We've already seen this. The mass of an object is the integral of density over the domain. So integral of 1 plus x dA. Because this is a circle, we will use our polar coordinates from the last lesson, and we will parameterize this circle. R goes from 0 to 1. Theta goes from 0 to 2 pi. 1 plus x then must become 1 plus r cosine theta. And dx dy, or dA, must become r dr d theta. And we now proceed to do this integral by iteration. First, we multiply through by r to get r plus r squared cosine theta. We now integrate in r, 1/2 r squared, 1/3 r cubed cosine theta. No contribution from r equals 0, so we plug in 1. It gives us the following. And now we integrate 1/2 plus 1/3 cosine theta. We get 1/2 theta plus 1/3 sine theta. Sine of 0 is 0, and sine of 2 pi is 0, so we get no contribution from this term, and all we have is 1/2 theta evaluated at 2 pi. So the mass of this object is simply pi. On the other hand, the center of mass is a different integral. It's 1 over the mass of the double integral of x times the density dA. We already calculated the mass. It's 1 over, so that becomes 1 over pi. And again, we parameterize this using polar coordinates. So 0 to 1, 0 to 2 pi of x times 1 plus x dA. Now it's just a matter of multiplying through and doing our integration. So we get r squared cosine theta, r cubed cosine squared of theta. We integrate in r, evaluate at 1, plug in, and we get some function of theta. This cosine squared of theta here must be turned into 1 plus cosine of 2 theta using a, 1/2 1 plus cosine of 2 theta using a half angle identity before we can integrate it directly. But once we've done that, we can now integrate each piece of this at a time. 1/3 sine theta plus 1/8 theta. When we integrate cosine 2 theta, we get a half sine theta, so we get a 16th sine of 2 theta. Again, sine of 0 is 0, sine of 2 pi is 0, and sine of 4 pi is 0. So we get no contribution from these sine terms and are left with simply 1/8 theta. That becomes pi over 4, and we divide by the mass to get 1/4. So indeed, the center of mass of this circle with more density over on the right-hand side is slightly to the right of the origin.